Okay, so we're going to be talking about Lewis structures or Lewis diagrams. They're simultaneous. So the way that we determine the Lewis structure of a chemical compound, we need to pay attention to the number of valence electrons. And, uh, and so we're going to count the total number of valence electrons on the compound that we're working with. Then we're going to put the electron that has the least electronegativity in the center of the atom. And the way that we do that, we kind of talked about the electronegativity last week. So we have that table that I share with you guys, and we'll be pulling that out here in a minute. So then the atoms that are typically more in electronegativity, they're going to be placed on the sides. And then our goal is to try to reach its octet, meaning that we want to get enough electrons around each of the atoms so that there's 8. Okay. And this is all atoms except hydrogens, and there are going to be some exceptions. And we'll talk about that here in a minute. And so after we've counted all of those electrons, we want to try to make sure that everybody reaches octet. Sometimes we may need to make additional bonds. A bond is going to be consisting of two lone pair electrons together, right? And then we want to check our Lewis structure. So again, we want to make sure that everything has 8 around it. Hydrogen is, again, an exception. It only likes to have one bond around it, okay? And then all the other atoms, they should have 4 pairs of electrons around it, or 8 electrons total. Okay, so let me show you what I mean. I feel like I'm in the middle of the talk. I feel like I missed one. Let's see. So in this case, we have nitrogen. And where is everybody today? Usually I have at least 8 people. So how many valence electrons do nitrogen have?
Is it 5?
That's right. It has 5 valence electrons. So we're going to put 5 dots around it. Okay. And a reminder, the way that we determine the number of valence electrons is that we're going to take a periodic table. How's your
Isn't it
week,
like
by the
the
way?
S or P subshell?
What was that?
Oh, isn't it the S or P subshell? Like
That's
both
right.
of
It's
them?
the S and the P subshell. That is correct.
And to answer your question, yeah, I'm all right. I've been all right.
Been all right? Good. Yeah, mine, I've had so many meetings this week, and I'm not done. That tomorrow I have like 4 meetings, 5 meetings tomorrow. I'm like, at some point I need to sit down and do grading and get caught up because I'm like so behind.
Aren't you like teaching like several different schools though besides Hartnell?
Yeah, yeah. I teach at Coalinga, and then two online courses on Coalinga, and then I teach one face to face, and I'm behind in all of them. So okay, there we go. Okay, so we see, so as you said, that's right. It's going to be the S and the P. So we know that this represents the S subshell, and this over here represents the P subshell. So we're just going to count over in that outer shell. So that's 1, 2, 3, 4, 5. So that's how we know we have 5 valence electrons. Okay, so let's go back. Okay, so then we know that hydrogen has how many valence electrons?
One.
1. Hydrogen is always going to be on the outside. It'll never be in the middle. because it can only form one bond. Okay, so we have 3 for hydrogen. So that's a total of 8 electrons. Okay, so for nitrogen to reach its octet, it needs to form a bond with this hydrogen. It needs to form a bond with this hydrogen, and it needs to form a bond with this hydrogen. So then that line represents 2 electrons. So that's 2, 4, 6, 8. Excuse me. I was trying to shove food down my face or my mouth earlier. So now it's deciding it wants to try to come back up. So 8 electrons. So nitrogen has reached its octet. Okay. And then hydrogen, because it wants to be like helium, it only wants to have 2 electrons around it. So it has 2 here, 2 here, 2 here. Okay. And then we have a lone pair electron. Okay. So if I have CH4, what would be the Lewis dot structure for this? And who would be in the middle?
The C, the carbon.
C. That's right. Carbon has how many valence electrons?
What?
Four.
4. That's right. 1, 2, 3, and 4. Okay. Hydrogen has how many?
One.
Okay. And we have 4 hydrogens, so each of them are going to have 1 valence electron. Okay. So in this case, we have 1 bond between the hydrogen and the carbon. So then that's 1, that's 2, 4, 6, 8 electrons around carbon. That's 2 around this hydrogen, 2 around this hydrogen, 2 around this hydrogen, and 2 around this hydrogen. Okay. So altogether, that should be 8 electrons, 4 and 4 total. It's going to equal 8. Okay. Do you guys see? Understand that? You see it?
Yes.
Okay, good. Okay, so here, draw the Lewis structure for hydrogen carbonate ion. Now, anytime that we see a minus charge or a plus charge, that means that if it's a minus charge, that means we're going to add an additional electron. If it's a plus charge, that means that we're going to remove 1 electron. Okay. And so typically what I do, I always like to add the electron to the middle or to the center atom. So who's going to be our center atom?
Carbon.
Okay. How many valence electrons does carbon have?
4.
4.
What's it called? The one with the weakest electronegativity usually goes in the center, right?
That's right.
Okay.
Okay. And then oxygen, how many valence electrons does oxygen have?
Is it 6?
Okay, that's right, 6. And we're going to have 3 oxygens. 3 times 6. Okay, and then we have one negative. So what does that mean?
We add one more.
That's right. We're going to add one extra one. Okay. And then hydrogens, we have one hydrogen, and that hydrogen has one valence electron. Okay, so now what we want to do, we want to try to arrange it so that we can get 8 electrons around everyone to make everyone happy. Okay, except for the hydrogen, which only wants 2 electrons. Okay, so we're going to maneuver this, right? And so if we do that maneuvering so that we can get 8, so we'll have carbon in the middle, say a bond here. So we'll take, we're going to change the color of our pen now. So we're going to take this electron, move it over here. So this one will pair up. We're going to take this electron here. Oops. Those 2 electrons there. And we're going to have that one paired up. And then we're going to take this electron down here, bring it over here. Okay, so, and if we do that, right, this hydrogen probably won't be on this C because then we're not going to be able to sit there and reach our octet. So what we're going to do is move this hydrogen and we're actually going to put it on this oxygen here. So then we'll take one of these electrons and put it over here. Okay. So let's see if we can make this mess look a little bit more presentable. So altogether, that's what, 8. That's 8 and 7. It's an odd number. Hold on. 1, 6 times 3. I'm sorry. I'm screwing up. 18 plus 2 plus 4. So 18 plus 6. So then that's 24. I mean, 22. No, 24. I can do math. 18 plus 6. Yeah, 26. Or 24, sorry. Try it one more time. Okay, so we have 24 electrons that we're working with. So we want to make sure that we have 24 electrons at the end. And so I said, we're taking this electron, moving it over here, taking that one, moving it over here. So we have one that's going this way. And that's going to be attached to the hydrogen. Okay, so if we look at this, does this work?
Yes.
Are you sure? So we have 2. Let me colors. So we have 2, 4, 6, 8.
I think carbon needs eight, right? Because it only
That's
has
right.
6.
Carbon only has 6. That's right. So what we're going to do is we're going to take one of these guys. We're going to take one of these lone pair, and we're going to bring it over. Okay. So then in that case, we're going to end up with a double bond. Okay, so this is this is 2, 4, 6, 8 around that oxygen. We have 2, 4, 6, 8 around this carbon. I have 2, 4, 6, 8 around this oxygen. And I have 2, 4, 6, 8 around this oxygen. Okay. What do you guys think? Does that work?
Yes.
Yes. Okay. So and then we got the 2 around the hydrogen. So everybody's octet is filled. So everybody's happy. Okay. Any questions so far?
No.
No? Okay. Ah, I forgot. So at the very end, because it had a charge on it, we're going to have to put the brackets around it, and we'll put the negative charge to remind us that we added an extra electron. Okay. I feel like I'm missing something. Okay. So the next thing that we want to talk about is called resonance structures. A resonance structure is just basically you have two Lewis structures that are going to be equal to each other or approximately equal to each other. And really, all that's happening is that the electrons are going to be moving positions. Okay. Um, and so really what's going to end up happening is because you have both of those structures that are going to be existing in nature. So one molecule may have one resonance structure, one may have another resonance structure. So really what you're going to end up doing is getting something like the average between the two different structures. And I'll show you what I mean by that. And then an isomer is going to be different than a resonance structure. An isomer is going to be basically, it's going to have the same molecular formula, but it's going to have different uh, structural formula or a different structure. Okay. And then because of that, it's going to behave different. I'm going to show you an example of that here in a second. Okay, so resonance structures. This is what we mean by resonance structures. So basically, if you guys take a look at this, this compound, this compound, and this compound. So in this case, um, we have it's I guess sulfur trioxide. In the case of the sulfur trioxide, we have double bond located on this oxygen here. Okay. So a resonant structure of that, it will be equal to what it is going to be putting a double bond on the carbon that's in the upper left-hand corner. Okay. So that would represent a resonance structure. So in other words, all you're doing is you're moving the electrons around. And so like over here, this bond here is basically being changed over. let's see, it's being, let's see, these electrons are going to be moving because the electrons are always mobile. So they're always going to be moving around. They're trying to find the most stable structure. They're going to, once they hit the most stable structure, they like to try to stay in that stable structure for a little bit, but they're going to be constantly moving. And so stable structures are lower in energy, so they're going to want to try to stay in that lower state as possible. But this is one form of that lower energy. This will be another form of that lower energy. This will be another form of that lower energy. And literally, all this happening is that these electrons are moving out to the outer corner. So that means that one of these guys, for sulfur to be happy, they're going to have to move a pair of electrons here. And so in that case, you'll get your double bond forming over in your left-hand corner with this oxygen. And then this guy would have 6 lone pairs around it. Now, the same thing is going to happen in this context where now we have these electrons moving back around this oxygen. That means that this guy's going to have to get a pair of lone pair to form a double bond here. So these guys are going to be moving this way. So then you're going to get the formation of this resonance. Now, these resonance structures are going to be equal in energy. So neither of them are going to have a preference over each other. They're all going to exist in nature. Okay. Okay, I got carried away. Let me take a step back. Seven. Oh, eight. OH. Okay, so this here uh, is an alcohol. And this alcohol has 3 possibilities that you can get from it, right? One of those possibilities is called isopropanol. Another possibility is called N-propanol. Okay, so these 2 guys are going to be isomers of each other. So they have the same chemical formula. They all have 3 uh, carbons, total of 8 oxygens, and 8 hydrogens and 1 oxygen. So 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and 1 oxygen. Same thing over here. 1, 2, 3, 4, 5, 6, 7, 8 carbons, 1 oxygen, and I mean, sorry, uh, 8 hydrogens, 1 oxygen, and 3 carbons. It's been a long day. Okay. Now, if you look at these, they are going to behave differently. Right. This one, since it has technically more surface area, right, its boiling point is going to be different than this isopropanol. So it'll take a higher temperature to make this guy boil compared to this one. Okay. Does that make sense? Can you guys see the difference between the two?
Yeah, they're made up of the same things, but they just have a different shape to it.
That's right. Yep.
So those are isomers, so they're different from resonance structures because resonance structures they're the same like shape,
Yes.
same like okay.
Yep. The only thing that's different in the case of the resonance structure is that where the electrons are going to be located. Okay. Okay. So let's move forward. Okay. So the next thing that we're going to be taking a look at, we're going to be looking at the electron pair geometry. So, often you'll see I write it as EPG, right? Electron pair geometry. So in this case, we're going to be looking at the number of electron pairs around a center atom. And then anywhere that we see lone pairs around the center atom, that's going to count as one electron pair. Um, or if it's attached to another atom, right? So let's say, for instance, if I had earlier, I had nitrogen with one lone pair on top, a hydrogen here, a hydrogen here, a hydrogen here. So the first thing that we want to do is determine how many things are attached to the center atom, including lone pairs. So the lone pairs in this case will add as an attachment. So this would be 1, this would be 2, this would be 3, this would be 4. So this has 4 things attached to it. So since there's 4 things attached to it, it's going to be called a tetrahedral. And that's going to be coming from the term tetrahedron. Tetrahedron means that it normally has 4 sides, 4 solid sides, in an equilateral triangle facing towards each other. So in other words, it's like if we drew a line, so we have my center atom represents that vortex here. So we'll have 1 here. We'll have 1 on top. Ooh, I almost screwed that one up. Hold on. Okay, so we have 1 here. We'll have 1 here. We'll have 1 here. Okay, and then technically you'll see that one in the back. So we have 1, 2, 3, 4 sides. And so we call that a tetrahedral. Right?
It's kind of like a pyramid,
Yes, it'll be kind of like a pyramid type
like you're
structure.
looking at it from above or something.
So in that case, let's see, get ahead of myself here. So here, this is an example of our tetrahedral. So they got the 1 on top, 1 here, 1 here, 1 here. So you technically have 4 attachments. So that this guy would be a tetrahedral. Okay. In this case, it has 3 attachments. This guy is called trigonal planar. Okay. Because there's 3 attachments And the angle of these guys are going to be 120, 120, 120. And they call it planar because it's going to sit in a single plane, like a single sheet of paper, you know. So, or do you guys have you seen a widget spinner? The one with the 3 points on them?
Yes.
Yeah. So it's kind of like that. It's in a single plane. You don't have anything coming up or anything coming down. So it's a single plane. So then that's the reason why we call it trigonal planar, because there's three things attached to it and it's planar. This one is going to be linear. And in this case, the angle is going to be 180. Okay. So linear, trigonal planar, and tetrahedral. Okay. Now, these are going to be your electron pair geometry. That means that we're looking at either electron pairs or we're looking at atoms that are being attached to it. We also have what we call our molecular geometry. Our molecular geometry is when we don't look at the lone pairs. So, but the lone pairs are going to affect our shape, but we're not looking at them as an attachment. So here, these are going to represent our electron pair geometries. And then these are going to represent our molecular geometry. This is what they're going to be looking like. So if I have two attachments, right, two things on, say, a center atom and two things attached to it, and like in this case, so we call that, again, it's going to be linear. If we have three things that are attached to our center atom, we call that trigonal planar. Three things attached to our center atom. Now, in this case, we have one of the things is going to be a lone pair, and then you have two atoms that are going to be attached. So in that case, this guy's going to look bent or angular. The reason why it's going to be bent or angular is because we're not looking at the lone pairs for the shape. We're only looking at the atoms that are being attached. Even though the lone pairs affect the shape, we only see the atoms. So in this case, this guy is just going to be bent. This is what you're going to see. Now, when we have our double bonds or our triple bonds under these circumstances, then we have it only counts as a single attachment because it's only attached to one atom. Does that make sense? It counts as four sets of electrons, but it only counts as a single attachment because it's only attached to a single. Okay. So in this case, we have four attachments to our center atom. So in that case, we have four atoms that are going to be attached to that center atom. So that's going to be tetrahedral. Sorry, not trigonal. Tetrahedral. Again, four attachments. In this case, one of them are a lone pair. So in that case, this guy's going to be called trigonal pyramidal. So that would be its molecular geometry, trigonal pyramidal. So in the case of the nitrogen earlier, with the three hydrogens, so that one would be an example of trigonal pyramidal. And then in the case of where we have two lone pairs attached to it, it's going to be bent and angular. So this is just like water. So hydrogen, hydrogen, and technically you have two lone pairs off of here. But we don't see the lone pair, so it just looks bent to us. Okay. So if I ask you, in the case of water, its electron pair geometry would be tetrahedral, but its molecular geometry is going to be bent or angular. Okay. Questions?
Wait, so with the double bond, it only counts as like one bond then? Is that
So
remember
it counts as
you
one
said something like that?
attachment. One attachment.
Yeah,
So
one
don't think of
attachment.
it as a
Yeah, yeah.
bond, but it counts as one attachment because
Okay.
it's only attached to one atom. Yeah. Okay. So here's methane. Methane is going to be tetrahedral for its molecular geometry. It's also going to be tetrahedral for its electron pair geometry because in the electron pair geometry, we take into consideration lone pairs. Okay. What about ammonia? What is it going to be? It's electron pair geometry.
A trigonal pyramidal.
That's going to be its molecular geometry.
Oh,
So
oops.
what we're going to see is just we're going to see just this part of it. We're not going to see that lone pair, right? So in that case, that's the reason why we call it trigonal pyramidal because it looks like a pyramid. So let's go back. So this is what it's going to look like. This is what we actually happens with the electron pairs, right? So this is just showing our electron pair. So its electron pair geometry is going to be tetrahedral. Okay. And then in the case of water, its shape is going to be bent, but its electron pair geometry is going to be tetrahedral. Okay. Now we're going to see if you guys want to test this out for you. Okay, what happened there? Do you guys see my whiteboard?
Yes, we see it.
You
Yes.
guys see it? Okay, good. Okay. Yeah, it is acting crazy. Okay, let's see if I can get it to work. So it's a new whiteboard on Zoom. So they've updated stuff. So you've got to bear with me. You guys are moving around everywhere. Okay, you guys ready?
Yes.
Okay. So let's see. Let's say we have carbon dioxide. Okay, so what I want you guys to do is draw the Lewis dot structure. Then I want you to tell me its electron pair geometry, its EPG, and its molecular geometry. Okay, so first thing that you want to do is draw your Lewis structure. Okay, so who's going to go in the middle?
Carbon.
Carbon.
Okay, and how many valence electrons does carbon have?
4.
6. No, 4. Yeah, 4.
Oxygen has 6.
That's right. So our oxygen has 6.
And then times 2.
And then that's 12.
So 16 total.
Yeah.
Thank you guys, because my brain is not functioning today. So 16 total electrons. Okay, so now we need to make it so that everybody has 8 around it. How can I do that? So are you guys moving? Because I see you guys, each of you guys moving your thing on the screen. It doesn't allow you guys to do anything else other
No,
than
that's
screen.
us moving the whiteboard around
It's
on
just like
our
a little
screen.
hand.
Okay. So you
Yeah,
guys have little hands.
I
Yeah.
do. Yeah.
Okay. Huh. Oh, okay. Wait. So you guys have little hands, right?
Yeah.
Select on your little hand. You guys see have a menu that has your hands like to grab. And is there a one that says select at the top?
No, I see all eyes on me. So I think that's just you presenting.
Okay. Okay. So I stopped presenting. Can you guys see a menu?
No, we're still viewers. You're the owner.
Okay. How can I make this? One person is following me.
If I do that. Can't really do anything else.
Hmm. Get a laser. Okay, so you guys can see my laser, timer, vote, presentation. I don't know what to do. Board. Board to project. Create cap, view, vote, find, export. And so you guys can see what I wrote on there, at least.
Yes.
Okay. Uh, it's weird. I don't know how to allow you guys to view. So who can see what I share here? Let me see if I can go to it. Earlier gave me the option of doing classic. See if I can get the classic. Okay, well, we'll go ahead and finish this one. So what do I need to do to this so that everybody has 8 around them?
Form bonds?
Okay, so how many bonds? So right now we have, that'll be 2, 4 around our carbon. Is that going to work for us?
No, because
No,
carbon needs 8.
because carbon needs 8. So what we're going to do, we're going to borrow a few from our oxygen
The double bonds?
to form double bonds. That's right. So we're going to get O, double bond. Okay, so what am I going to have to do on this side?
The same.
Same thing. Okay, so how many attachments, including lone pairs, are around the carbon?
2.
2, that's right. So if there's 2 attachments, 2 things attached to it, what is going to be its molecular geometry?
Is it linear?
Linear.
Linear?
It's going to be linear.
Linear.
That's right. So it's going to be linear.
So then the angle is 180 for the linear?
That's right. So our angle is going to be 180. Okay. Add a page. Okay, so that at least works. Okay, so if I have let me fix that. Where's the eraser? Sorry. Okay, so I don't see an eraser either. So, there we go. Okay, so this is acetate. Or I'm sorry, acetic acid. Sorry, it's acetic acid. So let's go ahead and draw the Lewis structure of this. Now, in this case, you could have you could have both carbons as their center atom. Okay, so let's go ahead and put one carbon as our center atom, and then we're going to have another carbon hanging out over here. Okay, so how many valence electrons does this carbon have? Can you guys hear me?
I don't
I
I
can't
don't
see your
see it.
formula.
You guys
I
can't
don't
see my
see it.
formula?
Yeah. Yeah,
No.
we just see the old one. It's
Yeah.
carbon dioxide.
Okay, how about now?
Oh, it's on a separate page. It's on page 2.
So you guys have to flip to page 2?
Yeah.
Oh, wow. I don't know if I like that. Hey, can you guys get
Uh,
to page 2?
yeah, it's in the around the bottom right by the leave button.
Do you just click on it, or how do you get to it?
Are you on
'Cause
PC or mobile?
on PC, on not PC, but on a Mac, on
There
a
should be
laptop.
like two little squares and it says like a one or it shows you like a number.
Oh yeah, it shows me the one. Okay, and let me click on it. Thank you.
Yeah.
Could you repeat the question, Professor?
Could you guys draw the Lewis structure for this guy? Actually, I'm going to change it real quick. Hold on. We'll actually use acetate. And it's a minus. Okay. Okay, so this is acetate. Okay, so who's going to be in the middle?
Carbon.
Carbon.
Okay, so in this case, we have two carbons. So we're going to put them like right next to each other. Okay. So, and carbon has how many valence electrons?
4.
Four valence electrons. Okay. So around one of the carbons, we're going to have three hydrogens. And then in the other ones, we're going to have our oxygens. How many valence electrons does our oxygens have?
6.
And then the minus means what again?
1 extra.
Okay. Okay. Yeah, one extra. Okay. Okay, so we need to draw the Lewis structure so that everybody has its octet filled. Okay. So right now we have, let's see, 2, 4, 6, 8 around this one. So I'm just going to go ahead and draw some lines there. First. I don't know if I like this. There we go. I don't know if I like that either. Man, they're really weird. There.
Does this one have a total of 25?
Okay, let's see. So we have 4, 4. And remember, we have one extra, right? Because of the minus charge, right? So
Yeah.
we got 4 for each of the carbons. So that's 4 plus 4. Plus 3 for each of the one for each of the hydrogens. And then we have 6 plus 6 plus 1. So that's 24. Is that what you got?
I think I just added one more because of the negative.
Yeah, we got the negative. So we have 3 hydrogens.
Okay, so it's 24. Okay.
Okay, let's see. Yeah, let me see if I can get my eraser to work because it's doing some weird things. I can't get this, just not wanting to erase. Okay, that works. That works. Okay, let me see if I can get my line drawn. It's so weird. Okay, so for this carbon, we have a bond with the hydrogen, a bond with this hydrogen, a bond with this hydrogen, and a bond between the carbon. So that would give me 2, 4, 6, 8 around that carbon. So that looks pretty good, right? Now, what about here with these oxygens? What's going on with this? What do you think we need to do? I can make this a little more prettier if it erases. Erases everything.
You said the total was 25, so that's
24.
an uneven, oh, 44?
24.
Oh, 24. Okay. What if it's uneven? So does that mean like one of them won't be able to like reach octet, right?
Yeah, that's right. The one that has the lowest electronegativity won't be able to reach octet.
So the one in the middle, right?
So, well, this one we have an
Technically.
even number, so we'll definitely be okay, right?
Yeah, but I'm just talking
But
about
if,
like
if
if
we were
like
short, yeah. So it doesn't necessarily have to, yeah. So typically it's going to be the one in the middle, unless there's hydrogens on the outside, right? Although, yeah, that should make a difference either. So it's typically the one in, because that's your one with the lowest, the weakest electronegativity.
okay.
Okay, so we have a electron up here. We have an electron down here. So where are we going to move our electrons so that we can reach our octet? So right now we have this one right here. So that would form a bond, potentially. These two over here. So what else am I going to have to do?
We can move the bottom electron on the bottom of the C to the top.
Okay, so let's go ahead and do that. So we're going to remove this one and put it on top. That's if it allows me to erase it. Okay, so now that gives us a bond here. Okay, so is that going to give us our octet around the second carbon? I mean, this carbon here
No.
right now. That's 2, 4, 6 around it. So what else do I need to do?
We could take one from each oxygen and put on a lone pair on the bottom.
Okay, so that we could try that. So we'll take one from each of the oxygens. Oops. Instead, put on a lone pair. Okay, so then what does that do to our oxygens? So that's 2. So we have 8 around the carbon, but then that's 2, 4, 6, 7 around this oxygen. And then that'll be 2, 4, 6, 7 around this oxygen. Is that going to work out for us?
No.
No.
Why
No.
not just move a hydrogen?
Well, the hydrogens are good over here, right? But if we move those over, then this carbon won't have its octet, right?
What about a double bond somewhere?
Ah, we could try a double bond. So let's take these away here and let's put a double bond somewhere. So that basically, if we do that, take those two, put it here, and then let's put one of those electrons back over here. Okay, so that's 2, 4, 6. Are those grids screwing you guys up with the, see if I can get rid of that.
A little bit, yeah.
Because it screwed me up. I am like, I don't know what the hell's going on. None. There we go. Does that help? Okay, there we go. You guys, it's no longer gridded.
It still shows a grid
It
for
still
me.
has a grid.
It does.
Yeah.
That's so weird. Because on mine, it doesn't. So maybe you can control yours. Is there like 3 lines? Do you guys see something with 3 lines? It says intro to chemistry. It has 3 lines on it.
It's on the top left with 3 lines.
Yeah. So
There's a
select that.
cloud.
Yeah.
Grids, none.
Yeah. So hit grid, hit none. So did it get rid of your
Oh,
grid?
yeah, that's much better.
Okay. Yeah. I don't know if I like this program. There's too much flexibility. Like, you guys can't write on anything, but or at least I don't know how to get you to write. So sensitive. It doesn't erase anything, but then it erases the thing that I don't want to erase. There we go. Okay. Okay, so now that's 2, 4, 6, 8 around this oxygen here. That's 2, 4, 6, 8 around this carbon. That's 2, 4, 6, 8 around that oxygen. That's 2, 4, 6, 8 around this carbon. And that's 2 around this hydrogen, 2 around this hydrogen, and 2 around this hydrogen. And then we have to, since it's a negative charge, we'll have to bracket it and put a minus. Okay? Okay, I'm going to put one more up and then we'll move on. Let's see, what time is it? Uh, I don't like when they do improvements in the middle of semesters. Okay, so we'll do one more and then we'll take a break. Okay, I'm going to add a page, so that means you guys need to go to the third page. You guys ready?
Yes.
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 Well, that's if my page decides to work. Okay, so we'll try it again. Okay, so this time let's do C H O. C2. There you go. C2HO. I mean CH2O.
So we have 12 valence electrons.
Okay, so we have 12 valence electrons. So we have 4 for carbon plus 2 for our hydrogens plus
A
6.
6.
So we're working with 12 electrons. Okay. Who's going to be in the middle?
Carbon.
Ooh. Okay. Who's going to be on the outside?
2 heliums. I mean hydrogen.
Hydrogens.
Hydrogen.
Yeah. Okay. And they have how many valence electrons?
They have 1 each.
One each.
Okay. Okay. And then our oxygen, we can either put on the top or the bottom. Okay. And it has how many valence electrons? You said 6 earlier. That killed me because you guys can move around. I see you guys moving around. You can't write yet. I haven't figured that out.
Oh, was there a menu option when you started opening the whiteboard?
Yeah, it pops up on my left-hand side for me.
Was there 2 buttons to check, like one to present and one to like let people annotate?
No, there's only well, there's technically there's 2 buttons.
Yeah. Could you read them to me?
It says select and then it's icons. It's a pencil and
Uh,
then the select button and the grab button.
because I found a video on the new Zoom YouTube channel. Uh,
Okay,
I'll put that in chat for now so you can see it later.
that'll be perfect. Thank you. Because my computer is too old and it can't do a lot of things right now. So it's struggling. Oh, wait a minute. There's also squigglies. Hold on. No, that's my laser. Okay. So what do we need to do?
Bonds.
Bonds. How many?
2 single and 1 double.
2 single. So the double is going to be between what? What 2 atoms?
Carbon and oxygen.
Carbon and oxygen. Okay. So we need a double bond here. Get my pen. And take that one from the top. Put a double bond. Okay. So now what is its electron pair geometry?
Like trigonal.
Trigonal. Yeah.
Trigonal what? There's two options. Pyramidal or
Planar.
plane? Planar, that's right. Okay, what is its molecular geometry?
Is it the same or is it the angular bit?
Do you have lone pairs?
No.
No. So then it would be the same.
And the angle on that one, would it be 120?
That's right. That's right. Okay. Okay, so let's take a break. Let's say you want to take a 10-minute break, bathroom break,
Yes.
and I'm gonna
That's
probably
fine.
make some coffee because otherwise I'm gonna
Wait,
die.
wait, 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 wait. Before you go, so does molecular geometry, is that just like the degree that it's in, like the angle, right?
No, it's also shape. So it'll be like the shape it's in. And remember, you don't see the electron pairs, right? We'll do one more when we come
Mm,
back and you'll see what I'm talking
okay.
about. Okay. Okay. So 10 minutes and then we'll come back and then I'll show you the one that I'm talking about. Okay, so now you guys see the classic one?
Yes, I see it.
And now you guys can write, right?
Yeah.
Yeah, good. And for mobile, you guys, your pencil will be in the corner. I think it's the left-hand corner if you're using mobile. Okay, so go ahead and let's go ahead and have you guys draw the Lewis structure for this and give me the molecular geometry and the electron pair geometry. Okay, perfect. Looks good. Somebody forgot their lone pair at top. So then what are we going to do? What's going to be its shape, its molecular geometry?
Is it the what is it called? Trigonal?
Trigonal,
Trigonal, pyramidal?
pyramidal. That's
Or
right.
pyramidal, yeah.
Like pyramid. That's right. Trigonal pyramidal. Okay, so then what would be its EPG? It's electron pair geometry.
Is it tetrahedral?
Tetrahedral. That is correct. That is correct. Okay. So tetrahedral because you have four attachments that are including a lone pair. And so when we talk about the electron pair geometry, we're always taking the attachments, what's attached to, as well as the lone pair. When we talk about its molecular geometry, we're ignoring the lone pair in terms of it affects the shape, but it doesn't affect the image because it's almost invisible to us. Okay. Okay, so let's get back to the lecture. Uh, struggling. You know, it's funny. I love technology, but I hate when I don't know how to get things to work. And when they do it new in the middle of a semester. There we go. Okay. Okay. So because often we don't have three-dimensional structures with us available, although you guys do have them with your kit. And for those in Hartnell, we will be playing with them this uh, Friday, this Saturday. So, so often we'll have to draw it, right? And so when we talk about the wedge uh, dash diagram, all it is that, let's say we're talking about ammonia. Okay, so we know that ammonia looks like this. Okay. And so with the wedge dash diagram, it helps us get a sense that something is a three-dimensional object. Okay. So if we take a look at ammonia, we have one that's going to be coming out towards us. One of the hydrogens are going to be coming out towards us and a little bit towards the bottom. So in that case, since it's going to be coming out towards us, we're going to make it a solid structure that looks like that. So typically fill it in. And so then we're going to put our H here. You're going to have one that's going to be going in the back. And so in that one, it's going to be the Wi-Fi signal as if it's going further and further away, right? And then it's going to have an H here. And then we're going to have one that's going to be in the same plane. Oh, I forgot my N. And then one that's going to be in the same plane. Okay, so the line represents it's in the same plane as our center atom. The Wi-Fi means that it's in the back. And then the wedge means that it's in the front. Okay. And then, of course, we got our lone pair. Okay, so that would be the example of the wedge dash diagram. Okay, so if we have nitrogen trichloride, go ahead and draw the wedge dash diagram for that. And I'll let you guys draw it, and then I'll put it on the screen. And then give me the molecular geometry and the electron pair geometry. So put your hands up when you guys are ready. So let me give you a hint. Is C the symbol for chlorine? There we go.
Cl.
Okay, good.
Could you guys help me write the dots? Like it's really hard for me.
Maybe. If my computer starts working.
Yeah, I'm on mobile, sorry.
Oh, that's okay. Okay, so if we're doing a wedge dash,
The regular one on the right, does that mean it's like on the side, right?
yeah, yeah,
Okay, and then the little wedge is the back, and then the triangle is the front. Okay.
that's right.
I did it like that, but like the opposite.
That's
Like,
fine. I mean, you can switch the one that's coming out towards you and the one that's in the back. It doesn't really,
oh,
that's okay.
okay.
Yeah. Long as one of them is representing the back and one is representing the front. Okay. So, and typically you don't have to worry about your dots. You don't have to show the dots because you're representing the symbol, how the symbol's going to look. So a lot of times you won't have to worry about putting your lone pairs around there. Okay. So it'll look something like this. That's the pretty picture. Okay. What is the electron pair geometry?
That is it the I can't even say it. Trigonal, pyramidal,
Trigonal, trigonal.
trigonal, pyramidal.
So not it's electron pair geometry. Because remember, it has the even though we're not showing the lone pair here, it has a lone pair up here, right? So how many attachments does it have? One, two,
Oh,
three,
it's
lone pair.
tetrahedral or something.
That's right.
Tetrahedral?
So it's tetrahedral. So the electron pair geometry is tetrahedral. And it's molecular geometry. You said it earlier.
The other
Trigonal,
one? Yeah,
Yeah. Trigonal,
trigonal. Wait,
pyramidal or something.
so what's the difference
pyramidal.
between electron
Pyramid.
pair and molecular geometries? Like I still don't get that.
Okay, that's a good question. So the difference between electron pair geometry is that in the case of the electron pair geometry, we're taking in consideration the electron pair, right? So you're looking at the electron pair. Molecular geometry is just looking at how the shape is going to be. So you're looking as if the electron pair isn't there. So you count the number of attachments and then you look at the shape. So in this case, it forms a pyramid, right? So in other words, if you have three attachments and a lone pair, that's going to be trigonal pyramidal. Always going to be trigonal pyramidal.
Oh, okay, so we're just looking at the same diagram in like different lenses, basically,
That's right.
right?
Yeah. So one is what you visually, what you would see with your eyes. And so that's what your molecular geometry is going to be. Your electron pair geometry, because we don't typically see electron pairs because they're so close to the atom itself, so we don't see them. So then the electron pair geometry is what is really happening because you have those lone pair electrons. Does that make sense?
Yeah, that makes more sense now. Thank you.
So in the case of the molecular geometry, the lone pairs are invisible to us, so we don't visually see them, even though they affect the shape. Okay, let's move forward. Okay, so sometimes we're going to have multiple bonds, like double bonds, triple bonds, and single bonds. So those guys are not going to affect that. We're looking at the attachments, as in the number of things that are attached to it. We're not looking at the number of bonds. Does that make sense?
Yeah, that makes sense.
Yes.
So in this case, oops, hang on, I went too far, too fast. So in this case, we have a double bond between the two carbons, right? So if we talked about the shape, the electron pair geometry for this guy would be what? We have a center atom. It has three attachments.
Trigonal.
That's right. Trigonal what?
Planar.
That's right. Trigonal planar. Because there's three attachments and there are no lone pairs, so it's always going to be trigonal planar. When there's a lone pair, we know that that's trigonal pyramid. Okay.
What's
And
the
so
other one besides planar?
what was that?
What's the other one besides planar?
Pyramidal. As in pyramid, pyramidal.
So planar is like kind of like if it's flat, and then
That's right.
pyramidal is like when it's 3D. Okay.
Yeah, when it's a pyramid. So it'll look like a pyramid. I know it's not the prettiest pyramid. This is why I'm not an artist. Okay. Okay. Polarity. So when we talk about polarity of the molecule, we're talking about the overall pull of the compound. Okay. And what I mean by that is, so if we had carbon dioxide, and we looked at the electronegativity of carbon and oxygen, we're going to look at them independently first. So if we have a bond between carbon and oxygen, so then we know that oxygen, if I remember correctly, is 3.4 and carbon is 2.6. And you're going to get that from that table. Let me pull it up. Oxygen is 3.4, carbon is 2.6. So that is a total of 0.8. We know that that's greater than 0.5, so it's a polar molecule. So in that case, the molecule is going to be pulling towards the electrons are going to be pulling towards the oxygen. So in other words, the electron is going to be moving in this way, in this direction. And this one is going to be pulling in the same way towards the other direction. Now, if the two are pulling in opposite directions, right, and they're equal pull, is anybody going to be able to pull anybody more? Have you guys ever played like tug of war?
Yes.
Yes.
Okay. Now, if both sides pull exactly the same, is the little tie in the middle, is that going to move in any direction towards one or the other if they're
No.
having the same?
No.
Right? So in that case, the molecule itself is going to be nonpolar. So this would be a nonpolar molecule. Okay. If I have S, C, O. Okay. So S is 2.6, carbon is 2.6. So that's going to be a 0 between the pull on that side. And then this side is going to be a 0.8. So in this side, it has 0.8 more strength than the other side. So then which way is the molecule or the electron going to be moving? Is it going to be
To
moving
the right.
oxygen? That's right.
Yes.
So it's going to be moving towards the oxygen. So then that means that this is going to be a polar molecule. Okay. Does that make sense?
Yes.
Okay. So let's say we have, let's do, Okay, we have FOH. Okay, so in this case, who has lower electronegativity? Who's going to be in the middle?
Oxygen.
That's right. Oxygen is going to be in the middle. So we have an F, O, and H. Okay. Which way is the electron going to be being pulled towards? Left or right? Or is it going to be nonpolar? Say, is it polar or is it nonpolar? Start off there.
Probably polar because fluorine has like a really strong pull.
That's right. So since fluorine has a strong pull, it's greater than 0.5. We know that it's going to be being pulled in this direction.
Yeah.
Okay. So we have a polar molecule. Okay. So I'm going to give you an analogy. It's going to be very crude because I'm really good at crude analogies. Okay. So let's say in this case, oxygen is a person who's currently dating, right? And hydrogen is like the crackhead, deadbeat, don't have a job. And fluorine is the doctor, right? Who will provide everything that oxygen needed. Okay. Now, who would oxygen want to spend more of its time? Fluorine or hydrogen?
I would hope fluorine.
I would hope so too, right? That makes sense. Okay. So that's the way we want to look at it. So the electron is going to be going towards fluorine because fluorine has more pull, it has more traction. Okay. So if we go through our lecture notes, go back to our lecture notes. Sorry, I'm talking to my computer because it wants to be difficult right now. It's like, nope, it's getting late. Okay, so let's say that we have Cl4, CH4, and then we have all the ones in between. So again, Cl is going to be like the doctor, right? And then CH is going to be, the chlorine is going to be like the doctor. The H is going to be the dead. Okay. So if we have all four CLs, so this doctor has uh there's a quadruplet, and they're all doctors, they're all dating you. Now, if you're that person in the middle, you want to spend time with all of them, try to get to know them all, right? One day with doctor number one day with doctor number two, one day with doctor number three, one day with doctor number. So in that case, nobody's favored over the other, right? They're all equal to each other. So then in that case, there's no net, we call it a dipole moment, or there's no net pull. So there's no polarity in that case. So that means that overall, the molecule is nonpolar. Okay. Now, if I have two doctors and one deadbeat, who am I going to want to spend more time with? The doctors or that one deadbeat?
The doctors.
The doctors. So then I'm going to spend most of my time between those doctors. I may give the deadbeat an opportunity every blue moon, right? So in that case, the net pull is going to be going in between the three doctors because that's the one I'm spending the majority of the time. Okay. So in the case of I have two hydrogens, two chlorines. So in that case, if I have two doctors, two deadbeats, I'm going to want to spend more time with my two doctors, right? So in that case, the pole is going to be going towards the 2-chlorine. Okay. And in the case of one doctor, 3 deadbeats, I'm going to want to spend more time with the doctor. Okay. So then in that case, the net pole is going to be going to, or dipole is going to be going towards that one doctor or CL. And then if I have only deadbeats, then there's no real preference, right? They're all the same. So in that case, there's no pole, no net dipole, which means it's nonpolar. Okay? How's it going? Do you guys see the analogy? Do you see how it works?
Yes.
Okay. So we did carbon dioxide earlier. We've already talked about it and the reason why that worked. In the case of water, water is a little bit different, right? Because there is a dipole between hydrogen and oxygen, but the electron is going to be going towards the oxygen. So in this case, both of them are going towards the oxygen. So the dipole moment is going towards the oxygen, right? And so that means that in that case, we get partial charges for the molecule. So the oxygen part is considered partial negative. The hydrogen parts are going to be partial positive because the electron is spending more time around the oxygen. And so it forms a net dipole moment towards the oxygen where the electron is spending more time around it. Okay? Now does it all kind of fall together?
Yeah, kind of. Does the dipole moment always like to go like in the opposite of oxygen? I mean, oxygen, hydrogen?
Yeah, because because we're thinking about it's the electron. The electron is moving, right? Electrons are moving. And in the case, since oxygen has a stronger pull for the electron, it's going to spend more time around oxygen than it's going to be spending around hydrogen. Another analogy that kind of works, and it may work a little bit better for you, is let's say you and your significant other gets a divorce and you guys have a kid, right? If the kid spends more time around you, right? That means that you have uh, the kid might be a pleasant thing and everything like that, but overall, the kid being a negative charge, it's going to make you more negative, right? Than in the case of your partner, who's going to be more positive, right? Because you're spending more time with that kid than your partner is. Okay.
Okay.
I'm sure your children are great and you love spending as much time with them as possible. Okay, so when we talk about organic chemistry, so this we're getting to the last part, the home stretch, and this is going to be real brief. I go over it in a lot of details, and if you guys look on Canvas, the videos for this, I went over it in a lot of detail in the past, but we're in crunch time, so I'm trying to get everything in, so help you guys remember the important stuff. And plus, some of you guys, if you need it, you'll be taking OChem next semester. When we talk about organic chemistry, it really applies to carbon, right? Carbon compounds. And carbon is, I like to say, carbon's a whore. The reason why carbon's a whore, and it's also the reason why it's the center of the life, is because it's able to have 4 attachments. It's kind of unlike anybody else. Silicone can actually technically hold 4 too, but carbon is the one that we go with, right? And it's able to have 4 bonds. And it enjoys to be in the center, so it's like the center point of a lot of things. And so because of that, we have a whole study that's dedicated to carbon, and we call it organic chemistry. So an organic compound is going to be a compound that has carbon, although there are exceptions, right? And often organic chemists will argue, no, they're really organic molecules, and then others will say, no, 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 they're inorganic. But these are going to be your exceptions for these purposes. Inorganic chemistry are all other compounds except hydrocarbons and their derivatives. So when we talk about carbonate, cyanide, oxides of carbons, and a few other really small carbon compounds are going to be exception. Okay. But everything else is going to be considered organic. Okay. So here is an example. We have alkanes. Alkanes are considered saturated hydrocarbons. Now, what that means by saturated, that basically means that the carbon has as many hydrogens as it can possibly take, right? So if you look at it, everything that is going to be attached to that carbon is going to be a single bond. It's considered to be an alkane, and it's considered to be saturated. Unsaturated means that you have a double bond or a triple bond with your carbons. Okay, so I'll show you an example of that by hand. So these are all examples of hydrocarbons. These are all considered alkanes, and these are all considered unsaturated hydrocarbons because they're only single bonds. Okay, so this one is called butane, right? Bute, the reason why they call it butane is because there's 4 carbons. And I'm going to go over this even though we're crunched for time. If we have 1 carbon, it's meth. If it's 2 carbon, it's prop. If it's 3 carbon, it's bute. If it's 4 carbon, it's okay, wait. Sorry, I screwed up. Sorry, that's 1. I forgot ethane. Eth. That's 2. Propa. That's 3. Or prop. It's late. Bute is 4. Pent is 5. Hept. Oops. Hex is 6. Hept is 7. Oct is 8. Known is 9. Dec is 10. Undec is 11. And dodec is 12. Okay. So if we have a single carbon and 4 hydrogens, we call that methane. If we have 4 carbons and 8 hydrogens, we call that butane. Now, when we talk about butane, right, there are 2 types of butane. So these guys are called isomers of each other. In both cases, they all have 4 carbons, 1, 2, 3, 4. They all have 8 hydrogens. So that's 2, that's 4, that's 6, that's 8. Did I screw that? 2, 4, 6, 8. Sorry, 10 hydrogens, not 8. And so over here, this is called isobutane, right? And that's 2, 4, 6, 8. I screwed up 10. And we're missing a leg out for this one. We should have one more. Is that right? 1, 2, 3. No, that's good. So yeah, we're good. 2, 4, 6, 8, 10. Okay. So chemical formula for both of these are exactly the same, but they have different structures. They also have different boiling points. They have different freezing points. When they react, they're going to react slightly different from each other. Okay. Here's another example. So these guys are all examples of pentane. So in the case of pentane, we have pent means 5, and we have 2, 4, 6, 8, 10, 12. 12 hydrogens. Okay, so 5 carbons, 12 hydrogens. This guy is called N-pentane because they're like numerically right next to each other. This one is called isopentane because they have little isolates on one side of one of the carbons. So you have we call it methyl, a methyl group hanging off here and a methyl group hanging off here. So that's the reason it's called iso. This guy is called neo, right? Neo as in new, but in this case, you have a center carbon and you have carbons that are all hanging off of them with 3 hydrogens off of each of those carbons. So 3 methyl groups. Okay. So again, these are all considered alkanes because they're all single bond, and it's all hydrocarbons. There's no oxygens in there. It's only hydrogen and carbon. Are you guys holding up? We're almost done. We got 5 more slides. 4 more slides. So when we have an OH attached to a methyl, or I'm going to say of a hydrocarbon, then it's considered an alcohol. So you guys know ethanol. Ethanol is drinking alcohol. Methanol is wood alcohol. You drink that, you go blind. Butanol, 4 carbons. Methanol only has 1 carbon. So ethanol would have 2 carbons. Okay, and with hydroxyl group hanging off of it, a hydrogen, and an oxygen. Okay. We also have ethers. Now, ethers are going to be hydrocarbons with an oxygen between another hydrocarbon. So these are 2 hydrocarbons that are together. So this guy would be called diethyl ether because in this case, there's 1, 2 carbons on one side. There's 1, 2 carbons on another side. So that would be your diethyl, that ETH for 2 carbons. Di meaning that you have 2 of those species, right? And it's an ether. So that basically means that there's an oxygen between those 2 hydrocarbons. Okay. So this would be its common name, diethyl ether. Its its um, its IUPAC name would be ethyl. I'm trying to remember. Ethyl oxy ethane. Okay. So when we are you guys still there or did I lose you?
I'm
No,
barely
I'm still
holding
here.
up.
I'm still here.
You're barely holding up. I thought I literally lost you because things start popping up. So we put an oxy to let us know that there's an oxygen in between. So the shorter chain, the shorter one will be the first part. So ethyl oxy, and then the longer one would be the ane on the other side. Okay. So in this case, this guy, its common name is called methyl phenyl ether. So methylphenol ether. Okay. So to name its IUPAC name, it would be methoxy or methoxy. Okay, going the wrong way. Sorry about that. Too many letters. methoxy, and then in this case, this is a phenyl group, right? So um, it's this guy's common name is benzyl. So it would be called benzene. So methyl benzene, methoxybenzene would be its special name. Now the ENE represents that there's double bonds in it. This benzyl basically, or benz, means it's going to be a ring where you have alternating double bonds.
What is doxy? Like, what's the doxy part mean?
The oxy, so
Yeah.
the oxy means oxygen. So you have an oxygen between it. Meth,
Oh,
oxy, meth means one. So there's a one hydrocarbon attached to the oxygen.
oh, I see, I see. So that's why it's in the middle
That's
between the
right.
meth and the, okay.
Yeah. And so over here, this guy would be called eth ethoxy ethane. There's two carbons that's going to be attached to an oxygen, and then you have another chain that's all single bonds, so that would be ethane. Okay, so there's two carbons and they're all single bonds, so that would be ethane. Okay, we're almost there. We're down to two slides, two slides. So carboxylic acid means that we have our our carboxyl group, and that's basically COOH. So in this case, you're going to have C double bonded to an O, and then you have OH. So anything that looks like this is a functional group. So it's going to be an acid. So it's going to be a carboxylic acid. That's the family that it belongs to. So in this case, this guy is called formic acid. And again, this is its common name, formic acid. And the reason why it's called formic acid is because attached to that carbon, we only have the hydrogen. Okay. Now it's its IUPAC name, because there's only one carbon there, we would call this methane ionic acid, because there's only a single carbon. Okay. This one here, we call it, its common name is acetic acid, which we also know as vinegar. But its IUPAC name, let me get down there. Another one. How many carbons are here?
Two.
Two. So what was the prefix for two?
Die.
Not di.
Bu? I can't
Remember
remember.
I said meth is one.
Oh,
Meth,
F.
yeah, that's right.
F. Mhm.
Okay. Meth one, F is two. Okay. So then we would call this guy ethanonic acid. Okay. This guy, it doesn't have a common name. It only has its IUPAC name. How many carbons do we have?
Three.
Three. So the prefix for three would be
Prop.
prop.
A
That's
prop.
right. So proponic acid. So that's what that would be called, proponic acid. Okay. So if I have eight carbons here, what type of acid would it be? I'll show you what it looks like. And also I'm gonna draw what we call the stick structure. So each one represents each end, or each vertex will represent a carbon. So that would be one carbon. This would be two carbons. This would be three carbons. This is four carbons. This is five carbons. This is six carbons. This is 7 carbons. This is 8 carbons. And then we're going to have a double bond on the 8th carbon. That's how you would draw a double bond. And it's attached to an oxygen. And then over here, it's attached to another oxygen and a hydrogen. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so if I have 8 carbons, what is the prefix for 8? What is that animal that lives in the sea that has 8 legs?
Oct.
Okay, that's right. Oct. We're going to call this guy octonic acid. Do you guys see how that works?
Yes.
Okay, so again, that's called IUPAC nomenclature. Okay, so these are some examples. Oh, we already did those examples. I don't know why I have it twice. What did I do? Yes, that's it. Okay. Okay, so any carbon that we have, any carbonic acid that we have, those are going to be weak acids. Okay. When we talk about weak acid, that means they only slightly ionize, they only slightly break up. So a lot of times they'll stay together, they won't break up into their individual components. Okay. So all weak acids only slightly break up. Okay. Questions? Concerns? Cash money? Okay, so I guess all the classes have one more exam. Then you guys will be free from exams for a while. Nomenclature is going to be on it. Molecular geometry is going to be on it. And the next topic is also going to be on it, which is going to be talking about moles, which we've already talked about before, the different types of chemical reactions, which we've already talked about, and ionization, which we will be talking about in more detail. Okay. Any questions? Are you guys tired? Ready for bed?
Yes.
Me too. I'm exhausted. I've been up since 4 this morning, so I'm exhausted.
Oh my gosh.
Yeah. So tomorrow's going to be a horrible day for me. I have 4 or 5 meetings in the morning, 4 meetings in the morning because one got canceled. And then I have my lecture for my other class. So, but I'm trying to get caught up and I'll try to have your grades done ASAP so that you guys know what you're going into for the next exam and the final. The next exam is going to be really close to the final for those that are in Kalinga. You guys in Salinas, I mean not Salinas, in Soledad, you guys have a little more time. So we'll be covering 2 more topics before you get to your last exam. So, and then of course there's the final, which covers everything. And of course, group presentations, which I have to put up your schedule so you guys can start signing up. Okay, I will talk to you
Dr.
guys.
I have
Yes.
a question. On the presentations, that's
Yep.
on Monday or on Sunday?
Your presentations that when you guys have to actually do it, or when is it due on the computer?
Or both? I didn't know there were different dates.
Well, there's different dates. So they're actually due the day before you're planning to present. So I'm going to give you that leeway. But you're going to have to sign up for a time that you and all your members of your group can actually make it. That plan to get grades. If you can't get in contact with people, try to get in contact with them, right? because it hurts you if they're not around. That means it's more work for you to do and all that stuff. And it
Yeah.
does, you guys are going to be deducted a couple of points for not having a full group.
Oh,
It won't, let's say you could still get an A if everybody shows up and does a great job. But if everybody don't show up, you're not going to get 100. There's no way you're going to get 100.
okay.
So,
Okay.
okay.
And the pages, when is the pages due?
So that's also due the day that you present. So everything's going to be due the day that you decide to present. If you decide to present, and I'm changing the week when everything is due because it was set up. It was planned to be set up so that the best presentations would have the opportunity to get some extra credit points and present at our symposium. Our symposium has changed, so that's not going to happen. We still may be able to get some of you guys, and what I'll do, I'll put your recording up for that presentation, and then you guys will have the opportunity to get, as I say, extra credit points for that.
Oh, okay.
Yeah.
Okay.
So you
So,
don't have to physically be there for it. I'd like you guys to be there for it, but you won't have to physically be there for it. But anyways,
okay.
okay.
Okay. And that presentation that you're talking about, that's the 20-minute presentation?
Yep.
Okay.
Minute presentation, 5 minutes of question and answers.
Yeah, okay. And then the video, like the music video, that one is due before
The same day, the day that your presentation is due.
or the same day. Okay.
Yep. So they're all due the same day. So I will give you a date, but that date really just depends on when you sign up to give your presentation.
What day we sign up? Okay.
Because they're going to be due the day before because I need it. I need a hard copy of it so that if something happens, then I have a hard copy to look at. So,
Oh, okay. All right. Sounds good.
I'll be sending messages on that. So if I get a minute. Any other question?
Do you have any like general tips on like what to study for the exam? Because I'm kind of lost on like what to like study for specifically because there's just like a lot to like cover, you know?
Study? Okay.
Yeah.
So my philosophy is, this is my philosophy, is uh I always go with the topics that I just covered. I would go through those first, right? And then I work my way back. And then how I go about studying is I look at the practice tests, right? I go through the practice tests. I do all the ones that I know I can do with no problems. Then I have the ones that I may need to brush up on, right? And then I have the ones that I have no clue to do. So the ones that I have no clue to do, how to do, then those are the ones that I go to those chapters, make sure I study those first because I need to fill in those gaps. And typically everything kind of relates together. So if you fill in those gaps, then some of the stuff that, I kind of work your way back, go the easy ones. So the ones I'm not so clear about, let's get those knocked out first. The ones that I'm more clear about, so I won't study as much on those because I've gotten enough on that. I'll do that at the very end when it's crunch time, right? Just brush up on it. The ones that I don't know, I know I need to put some time into, then that's the one that I'm going to probably start it first. Start that first, then the easy one, second one, the easier one, second. And then the ones that I know 100%, that'll be the last thing I study.
Okay, so just use like the like practice tests that you gave before, like use that as like a reference, kind of
Yeah,
like
I use that as a reference. Yeah,
like what to expect for the next exam.
that's right.
And then all the other extra stuff that you like teach us that too,
Yeah,
right?
yeah. So what I
Okay.
always, like I said, go back to the lectures. So the lectures that we just talked about, so those are going to be your priority because that's going to be the most points in the exam is the new stuff. The old stuff is
So the new stuff is more prevalent, right?
yes. But if there's
Okay.
something in the old stuff that you don't understand, it may affect what you know in the new stuff. Let's say, for instance, balancing chemical equations, right? So if you don't know how to balance chemical equations, you need to go back and learn that because you're gonna need it, especially on this new stuff, right? If you don't know how to use the periodic table, you're gonna need it. If you don't know how to do nomenclature, you're gonna need it. You know.
So would you say like the active learning would that be like a good practice if like I had to go back to any other chapters?
Yeah, that would be because the active learning is just kind of like it's a lot of questions of those two particular topics that we went over. Yeah. Yeah. So I would go back and anything that I said, I went through and I may have missed or that I had to do a couple of times to get it right, then I'd probably go to those first and look at those and try to figure out how to figure those out, you know?
Okay, thank you.
And then my philosophy is that I always try to do things, me personally, I try to do it myself first. Then if I can't do it myself, I'll talk to one of my classmates. If they can't help me, then I'll talk to the classmate that got the A, top three that are in the top three. That's what I would do, right? It's part of the reason why I give you the top three. Don't tell anybody since they don't show. Um, and then after that, I would um, I talk to the TA or the TA, and then I go meet with the instructor. If none of those can help me, then the instructor. And there's
And
a logic to it because you guys are more comfortable talking to your colleagues. Most of you guys hate talking to me. So I don't know why, because I think I'm cute and all and very friendly and uh,
Hey, Dr. Henry, for the labs, we have to take videos of ourselves doing them or like a picture?
so I would like to have you guys take videos of yourself doing them, but I didn't enforce it. So just get the labs done. That's my philosophy. But it'd be nice if you guys take videos and stuff. So
Okay.
I may add a couple of extra credit points.
Okay.
And especially if you post it on your Facebook, YouTube, or Insta pages, because
Okay.
that's how I get my business is through you guys.
Okay.
Because I'm not as cute as I used to be, so I have to use you guys to sit there and do it. So by you guys being cute, you get more business.
Gotcha.
Okay. Any other questions? I like this. I feel relaxed now. Maybe a little too relaxed. I'm about to fall asleep. Okay. Okay, if there's no other questions, I will talk to you guys. Uh, some of you guys this Saturday in lab, and the other of you guys either Monday in lab or sometime next week.
Yes.